Welcome back, everyone. So today I'm going to be doing a video on vector or linear independence and dependence. So why don't we get started? I know that was quite abrupt, and I haven't recorded in a few days now, simply because I've been fairly busy with schoolwork and the amount of work that I'm obviously receiving. So let's just get started. I just realized that it's actually white paper. It's pretty interesting. Let's switch to our regular paper. I don't like this. This is quite interesting. I'm not used to writing on white paper at this point. I've used this manila paper for so long now. It's amazing. But yeah, and also you'll be able to see that as our last video was on span of vector combinations and how that relates to vector combinations, you'll now see how linear independence or dependence relates to span. So yeah, let's just go. Obviously, let's start off with the title. You'll see my shadows, which is unfortunate, but linear in, just gonna abbreviate this indep. And yep. And what I want to start off with is to just introduce just a set of two-dimensional column vectors, right? So let's look at this set. Let's say we have -3, and how about, let's add that. -3 and 4 here, and the other vector, let's say we have -9 and 12. So that's our second vector. Now you might see these vectors and you might see a relationship, right? You can see that this vector here is 3 times that of this column vector here, right? It's just this scalar multiple of 3. So automatically, well, let's just write this down. So let's write this as a linear combination. So we can say, if we want to express this in linear combination, we can say C1 times -3, 4. But we can rewrite the second term as C2 times 3, since it's a scalar multiple of 3, -3 and 4. And you can factor out this vector here, -3, 4, such a way to make it look nicer. So you get C1 plus C2 times 3. And you factor out the vector -3, 4. And what you can see here is we're left with some arbitrary combination, linear combination of these two constants. And we can kind of treat this as some other arbitrary value, like C3, for example. So we can, this is nothing but some arbitrary value. If you plug in values, you get some arbitrary value C3. Gosh, I'm bad at pronouncing this. It's like a tongue twister, quite literally. And then you get this. And then what we explored in the past videos is that if you multiply constant by some vector, in this case we can plot this vector. So -3, 4. You can plot this vector in such a way, and you can see that if you multiply any arbitrary value by C3, what you can do is you get all types of points on this line. So you can see that we had 2 vectors, but we just ended up with a line. So this means that this vector is actually a dependent vector, or a dependent set, meaning that you can take some linear combination of one of these vectors here, and you can turn that into this vector. So in other words, it's kind of just like a redundant way of describing a line. Right? All you have to do is to describe a line is all you have to do is multiply some constant by some vector v, for example. That's the most simple way of defining a line. So in other words, you can say that the span of this vector, the span, let's say v1 and v2, vector 1, v2, v1, v2. All that is just this line here. It's just that line. So it's just a redundant way of describing the line, like I said. So just to further clarify, you can't find any C3 for which you get some, you can't ever break out of this here. You can't ever break out of this. On the contrary, if we take the set, I don't know, of two vectors, again, two two-dimensional vectors, 2, -3, 5, -2. And this is simple, right? You can easily see if these are independent or not. Oh, by the way, I haven't defined independent. Well, we've defined dependent. So independent is just if it's not dependent. So that's the simple way of thinking about it. Independent vectors can be easily seen if you plot them. If they're independent, they're not collinear. In other words, they don't lie along the same line. In other words, they're not scalar multiples of each other. So you can see that you can't multiply this vector in any way to get either one of these vectors. So it's quite obviously independent. This set is independent. The set of two vectors is independent. And we can easily see that by further graphing this. Can utilize that space a bit. So graph both points. 2, 3. 2, -3, my bad. And then 5. 5, -2. Right? You can obviously see that they have nothing to do with each other, right? But we can also see that this is actually quite an efficient way of describing this entire plane, right? This span of these two vectors is just the span of, I don't know, v1 again. We'll just use these same terms here, and v2. Span of v1 and v2 in this case is actually the entirety of R2, the entirety of this real plane, all real values within this plane, right? Because you can see, as we showed in the past videos, you can see you can multiply these. You can basically scale these up as much as you want and add them as much as you want, and you'll get all the values. Any vector, if you name any vector, you can find some combination of these to get to that vector. And we showed that in, I think, the most recent video besides this one. So now let's actually look at another example. This time we can utilize 3 vectors. So let's say we have vector -5, 6, and vector 3, -4, I guess, and then vector 2, -2. Interesting, right? So this is our vector 2, -2, or these are all our vectors, the set of 3 two-dimensional vectors. And instantly, what you can see is that it's going to be, it's either way, it's going to be dependent. Even if but obviously there is some relationship between these two values, right? You can say that v1 plus this vector v2 is equal to this vector v3, right? That's pretty obvious. But either way, what I want to express to you is that we can obviously see that because of this relationship, this vector has to be dependent between these values, meaning that. But to be honest, if you have any set of 3 two-dimensional vectors, it's always going to be redundant, right? If they're all two-dimensional, you'll have, for example, these two vectors, right? These two vectors lying here, and then you'll have some other vector here. Could lie across one of these lines, I don't know. Could be anything. And it's bound to be redundant because you can express these two vectors, you can combine them in some way to, for example, like this, to actually get this vector here. So either way, you can find some linear combination. If two of these vectors represent R2, meaning all the vectors in R2, you can actually just, it's going to be redundant, obviously. So actually, I'm going to try giving you a visual representation. So I'm going to try drawing a bit of a plane here. Let's say we have our two major axes. You can have two vectors here, right? And these form a great basis for R2, right? And basis I'll later define in later videos. But then if you see, this is the best way to define R2, right? Some combination of these two vectors will get you this entire plane, which stretches out infinitely, right? But then if you add any other vector along this plane, it's going to be redundant. You're going to get a dependent set of vectors. So you can have infinitely many vectors in there, and it'll always be dependent. The only way to get all independent values is to only regard these axes right here, and then take a vector up like this, which breaks out of the plane. So you can't get any combination of these two vectors to get to this. And now this forms actually a basis in R3, as you can see. Forms a basis in R3. So to describe R3, you have to actually break out of R2, obviously, to add a higher dimensionality to the mix. So let me give another example. It should look familiar if you take physics. Or it's not going to be exactly, but it should be should give you some deja vu. So we have a set of three-dimensional vectors. Three-dimensional vectors. Maybe -4, I don't know. So what do you think? Is this independent or dependent? And this is pretty obvious. Well, they're quite obviously independent. Not only because you can see that it doesn't take many steps to actually convert them into unit vectors, your I hat, k hat, and j hat unit vectors. Unit vectors in physics. But you can also see that in order to get to here, you can't really multiply by 0, otherwise you'll convert. Otherwise, you obviously won't be able to get to -4. You also can't you have to scale them somehow. So if you add these two together, you're obviously not going to get this. These two terms are 0. So since there are this many zeros, you obviously won't be able to. They obviously have no relation to each other, other than covering the entirety of R3 with some linear combination of them. So they might look something like, I don't know, we can say that this is our x-axis, and this is going to be our y-axis, and that's our z-axis. So x-axis is like 1. It could look something like, this could look something like this. Right. This is perpendicular. Anyway, it could look something like that, right? And you can just simplify that to your everyday unit vectors, which form a wonderful basis for any dimensionality of the reals. So hopefully that was a good summary it was just a basic introduction, very basic introduction to linear independence and dependence. But in the following videos, I will actually give a more formal definition of what linear independence and dependence is. So hopefully you enjoyed this video, and see you in the following videos. Bye-bye.